Hello and welcome back to the course on Introduction to Solid-State Physics. In the last lecture, we discussed the Kronig and Penny model, according to which we observed for the first time the existence of the forbidden bands in a solid. And later on, we will use this Kronig and Penny model to distinguish between the metals, insulators and semiconductors. This forbidden band could be arrived by considering a periodic potential of certain strength. Now in today's lecture, let us try to interpret this band diagram, the electronic band diagram, and what information we can derive from the band diagram. That is what we are going to see, and we are mostly going to focus on the dynamics of the electron, what kind of picture we can get regarding the motion of the electron wave packet inside the solid from the band diagram that we are going to discuss. We know that the electrons are basically the wave packets from the de Broglie's hypothesis. Any moving particle can be associated with a matter wave, and a collection of matter waves with a slightly varying frequency, which is what corresponds to a wave packet. Any realistic particle can be described by a wave packet, and the motion of this wave packets is associated with the group velocity, which is defined as d omega by dk. K is the wave vector and omega is the angular frequency associated with the motion of the wave packet, and this group velocity is responsible for the transmission of the energy. So rather than the phase velocity, the group velocity is physically much more significant. So we will see what information we can obtain regarding the group velocity of the wave packet and the acceleration and the effective mass of the charge carriers from the electronic band structure. And this is what is called as the electron dynamics, how the electron is moving, what is the velocity, what is the acceleration, what is the associated mass, the effective mass. That is what we are going to obtain from the electronic band structure. So now let us go back to our conventional reduced zone scheme, where you can see this kind of energy bands. This is the E versus K plot. These are the corresponding energy bands, and we can see at the edge of the Brillouin zone this band is flat, and at that point we observe the existence of the band gap. So there are two kinds of structures we can see, one is downward and other one is upward. And the electron wave function, the wave packet can be represented as psi rt is equal to psi r into exponential minus I omega t. So using this kind of function we can describe a stationary state. Here psi r is the spatial part and exponential minus I omega t is the time part. Now as we discussed the group velocity of the wave packet, let us write it as v instead of vg. Let us drop this index g here. So vg is equal to v. We know it can be written as delta omega by delta k. In this case, k is a three-dimensional vector which is defined in the reciprocal space. So the group velocity can be represented as delta omega by delta k. Further, we know that the energy of the electron can be written as h cross omega, and this delta omega by delta k, if you write it properly, this can be represented as the gradient in the k space, that is delta k of omega. And what is delta k? It is the gradient in the k space. We know in the normal Cartesian coordinate system, this gradient is represented as I cap delta by delta x, j cap delta by delta y, k cap delta by delta z. Similarly, in the reciprocal space, we can represent this gradient delta k as I cap del by del kx, j cap del by del ky plus k cap del by del kz. So this del omega by del k in general also can be represented mathematically as delta k of omega. And what is omega? Omega is basically 1 by h cross of E. This factor is a constant, so we can write this velocity v as 1 by h cross gradient in the k space of the energy of the electron, or we can also write it in this manner, 1 by h cross delta E by delta k. And we know that this parameter or this parameter represents the slope of the E versus k diagram. So it represents the slope of the E versus k diagram. So we can conclude that the slope of the energy band diagram represents the velocity of the electrons inside the crystal. Of course, there is a constant factor multiplied with this, which is 1 by h cross. But basically the slope is related with the group velocity of the wave packet associated with the moving electron inside the crystal. So this is what the slope of the E versus k diagram represent. Now if we plot it, so this is how there are two kinds of bands here, concave upward and concave downward. So let us first focus on this part. So at this point we can see the slope is 0. So we can start from here. Slope is 0, then slope is positive and gradually it is increasing, and at this point the slope is maximum. So slope is positive and gradually it is increasing, and at this point the slope is maximum. Now after that the slope is decreasing, but still it is positive, and at this point it is flat. So again it is 0. So this is the portion which is represented as the slope here. Now let us look at the other side. So this region. So here we are starting from 0, then it is having a negative slope. The E versus k diagram is having a negative slope from here, and it is gradually decreasing. Negative side it is gradually decreasing, and it is the minimal at this point with a negative sign, and again it is increasing and becoming 0. Similarly, for the other curve we can see, so here the slope is negative, becoming negative maximum at this point, and then again it is becoming 0. After that it is becoming positive maximum at this point, and then it is becoming, again it is reducing and becoming 0 at the zone boundary. And this slope is related with the velocity of the wave packet. V is equal to delta E by delta k. This also multiplied with a constant factor. This will give you the proper group velocity of the wave packet. and in this indicial notation we can write it also as Vi is equal to 1 by h cross delta E by delta K. Instead of writing Kx, Ky, Kz, can represent the ith component of the velocity to be 1 by h cross delta E by delta Ki. Now let us look at what this wave vector represent physically. We know that this when you multiply this wave vector with h cross, the dimension is that of the momentum, and this momentum is called as the crystal momentum. And what is the meaning of this crystal momentum? We know that the electron is moving inside the crystal. And when we apply some external force, for example electric field or any other external force, then this external force is related with this crystal momentum through this relation h cross dk by dt. Remember, it is only the external force, the rate of change of the crystal momentum is related with the external force, which is, but in case the solid, inside the solid, the electron is experiencing so many other internal forces, so it may not be the total momentum of the electron. So it is only related with the external force applied to the electron. Whereas if you take a metal, in case of a metal, we are having the free electrons. Free electrons, we assume that they are not being acted upon by any kind of internal forces, and in that case this crystal momentum will be the actual momentum of the electron. But in general, for the semiconductors or insulators, the crystal momentum is not the actual momentum of the electron, rather the rate of change of the crystal momentum is equal to the external force applied on the electron. So we can write this relation Fe is equal to dP by dt, which is equal to h cross dk by dt. Once again I repeat, this momentum is equal to the actual momentum of the electron only for free electrons. In general, it is not the momentum of the electron. So with this information, let us look at the acceleration of the electron. We know from the classical mechanics that the acceleration and the force are related through the Newton's law of motion, that is 1 by m into f. So let us try to have this kind of expression for the moving electron inside the solid. By doing that, what we will get is, we will get some information about the effective mass of the electron, which is related with the EK diagram. Now the slope of the EK diagram is related with the velocity of the electron. Now let us try to find out how the effective mass of the electron can be related with the EK diagram through this analogy. So for that, let us try to find out what is the acceleration of the electron, and we will incorporate this information that the rate of change of crystal momentum is equal to the external force experienced by the electron. So A is equal to rate of change of velocity, that is dV by dt, and V is, we know it is 1 by h cross delta E by delta K, and this relation 1 by h cross can be taken out, and through the cyclic formula it can be written as delta by delta K of delta E by delta K into dk by dt. Why we are doing this? Because We know that F external is h cross dk by dt, and our aim is to relate the acceleration with the force, so that we can get an idea about the effective mass of the electron. That's why we are trying to get this kind of expression in the acceleration. Now 1 by h cross delta by delta k, delta E by delta k, dk by dt. Now let us write the ith component of the acceleration, and we know that the ith component of the acceleration will be affected by all the components of the force experienced by the electron. So ai, which is equal to dvi by dt, is equal to 1 by h cross. We have to sum it over all the components of the k vector, that is dk by dt, that is dkj by delta t, and here also delta by delta k, delta E by delta kj. So we have to sum it over all the components of the force. So here we are multiplying h cross and dividing again by h cross through this relation. So it will be summation over j delta square E by delta ki delta kj into h cross dkj by dt, and we know this is nothing but the jth component of the external force. It is the jth component of the external force. So ai can be written as 1 by h cross square summation over j delta square E by delta ki kj fej. Remember, here k is a vector, so we cannot simply write delta square E by delta k square. If we do that, then we are assuming that the energy is the solid is completely isotropic in nature, but that is not the case. Due to the anisotropy nature of the solid, we have to write it as delta ki delta kj. So the relation is ai is equal to 1 by h cross square summation over j delta square E delta ki delta kj into fej, and it is classically analogous to the Newton's law of motion, that is a is equal to 1 by m fe. On the left hand side we are having the acceleration, the right hand side we are having the force, and rest of the terms is the reciprocal of the mass. And since this is a quantum mechanical entity and it contains the information about the effective mass that is experienced by the electron, that is governed by the electron when it experiences this force Fej, that's why it is given as it is written as m star, which is the electron effective mass or the carrier effective mass. So we can define the mass in this manner, and remember, here mass is no more a scalar quantity because it depends on the indices I and j. Here I and j are basically Cartesian coordinate, they are the x, y and z component, right? So mij star can be written as the reciprocal of 1 by h cross square delta square E by delta ki delta kj, so that this expression is satisfied, and this mass is called as the effective mass, carrier effective mass. It is not the classical scalar mass that we often deal with, it is the quantum mechanical entity, and it is related with the curvature of this E versus K diagram. This parameter is what? It is the curvature of E versus K diagram. The slope is delta E by delta K, and delta square E by delta Ki Kj will be the is called as the curvature of the E versus K diagram. And the effective mass will be a tensor of rank 2. So different direction, it is having different components. So we can write this as a column matrix A1, A2, A3. This is A2. So this A1, A2, A3 can be written like this: 1 by M11 star, 1 by M12 star, 1 by M13 star. You can think it as XX, XY, XZ, YX, YY, YZ, ZX, ZY, ZZ times the three components of the external force: Fex, Fey, Fez. In this way we can define the carrier effective mass of the charge carriers moving inside the solid, which contains information about all other internal forces acting on it. Now let us try to plot the curvature and get an idea about the electron effective mass. So let me draw two plots here. Suppose this is the E versus K diagram. I will come back to this little later. So this is the E versus K diagram. Suppose we are having two plots. One is like this and other one is like this. Then the curvature of this will be high compared to the curvature of this red plot. This red diagram will have lower curvature than the blue plot. So the effective mass, suppose this is A. So the effective mass corresponding to the electron for this band diagram will be less than the effective mass corresponding to this red band structure. Suppose this is B. That means the flat bands are having heavier mass than the narrow bands. Narrow bands are associated with lighter charge carriers, whereas the flat bands are associated with the heavier charge carriers. So flat band are heavy carriers and narrow bands are having lighter charge carriers. Now let us come back to the EK plot and see how the curvature of this EK plot looks like. Then we will see how the reciprocal of the curvature will appear. So up to this we have already done. This is the velocity of the slope of the EK diagram for these two bands. Now we have to take one more derivative for this. So here let us take one example here. Let us focus on this part. This is the slope corresponding to this part. So now we are starting. This is having here at this point, it is having the highest slope. So we have to start somewhere from here, and the slope is gradually decreasing, becoming 0 at this point, becoming 0 at this point, and then again it is negative, and gradually it is increasing and again becoming maximum at this point. Similarly, we can plot the other half of this. So for the other band, this is the other band. You can see same kind of mirror image can be drawn. So this is actually the curvature of the EK diagram for these two bands. Now curvature is not directly related with the effective mass, rather it is the inverse of the curvature, the reciprocal of the curvature, right? So you have to take the reciprocal of this curve. So the reciprocal of this curve, if take 1 by of this curve, then it will appear like this, and at this point it is 0, so it will be extended like this, like an asymptote. This 1 by 0 will be infinity, then again it is starting from asymptotic limit, then it is becoming here, at this point it is minimal, like this it is going to vary. Similarly on the other side, for the other band also the same case, asymptotically it will negative, then like this. So this is how the effective mass is linked with the E versus K diagram from here. So today we got two information. The slope of the EK diagram is related with the velocity of the wave packet of the electron wave, and the reciprocal of the curvature of EK diagram is related with the effective mass of the charge carriers. But remember one thing that we should see here is that, suppose look at this band, here the curvature is positive, whereas here the curvature is negative. Curvature is negative, that means the effective mass is also negative. So from this idea we can define or we can obtain the concept of hole. Which is the other type of charge carriers in case of, which are present in case of insulators or semiconductors, which we will be discussing in the next lecture. Thank you.